Welcome! In this session, we'll explore problem number 1506, find root of N-Ary tree. This is an interesting problem that challenges us to identify the root of an N-Ary tree using a clever algorithmic approach. Let's dive in and uncover the solution step by step. In this problem, you are given all the nodes of an N-Ary tree in the form of an array of node objects. Each node in the array has a unique integer value, and the array represents the entire tree, meaning no nodes are missing. However, the root node is not explicitly identified. Each node object includes two attributes, the val, which is the unique integer value of the node, and the children, which is a list of other node objects representing the children of the current node. Your goal is to write a function that can determine which node in this array is the root of the tree. The input will be the array of these nodes, and the output will be the root node object itself. To make this clearer, let's look at an example. Suppose the input is an array of nodes like this: node 1, node 2, node 3, node 4, node 2, node 3, and node 4. The output should be node 1, node 2, node 3, node 4, which is the root node of the tree. The structure of the tree can be visualized as a single parent node, 1, with 3 children, 2, 3, and 4. From this, it's evident that the root node is the one that does not appear as a child under any other node. Now consider another example where the input array contains these nodes: node 5, node 4, node 6, node 4, node 2, node 6, and node 2. The output in this case is node 5, node 4, node 6, which is the root node. The tree structure visualizes the root node 5 having 2 children, 4 and 6. Additionally, 4 itself has a child, 2. Here, node 5 is identified as the root because it is not a child of any other node in the tree. In both examples, the root node is identified as the one that has no parent. This observation is key to solving the problem efficiently. The constraints of the problem state that the tree will contain between 1 and 50,000 nodes, and every node has a unique value. The tree structure is guaranteed to be valid, meaning there are no duplicate edges or disconnected components. Some edge cases to consider include a single node tree, where the only node is the root, trees with deep hierarchies resembling a chain-like structure, and wide trees with many children at a single level. The unique property of the root node not being a child of any other node will help us devise a solution that works efficiently across all these scenarios. To start, let's consider a brute force approach. The core idea here is to use the property of the root node being the only node that is never referenced as a child by any other node. Based on this, we can identify the root by iterating through all the nodes in the tree and checking if each node is present in the set of child references. The process involves 3 key steps. First, we create a set to store all the nodes that are referenced as children. Then, we iterate through each node in the tree and add its children to this set. Finally, we check all the nodes again to find the one that is not in the set of children. That node is identified as the root. While this approach is simple and straightforward, it has significant limitations. The time complexity is n squared, because for every node we have to compare it with all the children in the tree, which results in nested iterations. This makes it inefficient for large trees. Additionally, it requires n space to store the child references. So, while it's easy to implement, it's not practical for scenarios where performance is critical. Now, let's move on to an optimized approach that leverages the XOR operation. XOR has a unique property: it cancels out duplicates, which makes it perfect for identifying the root node. Here's the intuition: if we XOR all the node values and all the child values in the tree, the duplicates will cancel each other out, leaving only the value of the root node. This works because the root node is never referenced as a child and thus has no duplicate. To implement this method, we start by initializing a variable XOR_sum to 0. Then, as we iterate through the tree, we XOR the value of each node and XOR the value of all its children with XOR_sum. After completing this process, the value left in XOR_sum will be the value of the root node. At this point, we perform a second iteration to locate the node with this value. This approach is highly efficient, with a time complexity of n, since we only iterate through all nodes twice. It also has a space complexity of 1, as we don't use any additional data structures apart from the XOR variable. The trade-off is that it requires an understanding of XOR operations, which might feel less intuitive at first, but the efficiency gains make it worthwhile. Additionally, there are alternative approaches worth mentioning. One option is the hash map counting method. Here, we use a hash map to count how many times each node's value appears. Nodes that are referenced as children will have multiple occurrences, while the root node will only appear once. This method has a time complexity of O(n) and a space complexity of O(n), as we need the hash map to store counts. While it's easier to grasp conceptually than XOR, it's less elegant due to the extra data structure. Another alternative is the degree-based approach. This method involves tracking the integree of each node, which is the number of times a node is referenced as a child. The root node, having no parent, will have an integree of 0. Like the hash map method, this approach has O(n) time and space complexity. It's clear and straightforward but requires maintaining an additional data structure to track integrees. Both methods are viable, but they involve extra space and don't match the simplicity of the XOR method. Ultimately, we chose the optimized XOR method as the best strategy for solving this problem. Its simplicity, elegance, and efficiency make it stand out. The key insight is that the root node is the only node not referenced as a child, and XORing all node values and child values eliminates duplicates, leaving the root's value. This approach minimizes space usage since it avoids additional data structures, keeping the space complexity at O(1). It's also highly efficient, with a time complexity of O(n), making it ideal for large input sizes. While the alternative methods, like hash map counting or degree-based tracking, are functional, they require extra space and lack the streamlined elegance of XOR. The brute force approach, while straightforward, is too slow for practical use on larger trees. The XOR method strikes the perfect balance between efficiency and simplicity, making it the optimal choice for this problem. To solve the problem of finding the root of an N-Ary tree, we first need to understand the structure of the input. The tree is represented as a set of nodes, where each node has parent-child relationships. The root node is unique because it is never referenced as a child by any other node. With this in mind, a brute force approach can be used to identify the root. The intuition behind this method is simple: if a node is not found in the list of children across the tree, it must be the root. To implement this, the tree is represented as a list of tuples, where each tuple consists of a parent and a child node. For example, the input 1, 2, 1, 3, 3, 4 indicates that node 1 is the parent of nodes 2 and 3, while node 3 is the parent of node 4. From this representation, we can systematically determine which node qualifies as the root. The next step in our approach is to extract the nodes from the input. This involves creating two sets, all_nodes, which will store every node in the tree, and child_nodes, which will specifically store nodes that appear as children. To populate these sets, we iterate through each tuple in the input list. For every tuple, both the parent and child nodes are added to all_nodes, while only the child node is added to child_nodes. Once these sets are ready, the root node can be identified. The root is the node in all_nodes that is not found in child_nodes. This is computed by subtracting child_nodes from all_nodes. If this subtraction results in a single node, that node is the root. However, if no node or multiple nodes remain, the input is invalid, as it does not represent a proper tree. Finally, we return the root node if it exists, or an error message if the input is invalid. Let's go through an example to see how this algorithm works step by step. Consider the input 1, 2, 1, 3, 3, 4. We start by initializing two empty sets, all_nodes and child_nodes. Now, we process each tuple. For the first tuple, 1, 2, we add both 1 and 2 to all_nodes, and only 2 to child_nodes. For the second tuple, 1, 3, we add 1 and 3 to all_nodes, and only 3 to child_nodes. For the third tuple, 3, 4, we add 3 and 4 to all_nodes, and only 4 to child_nodes. At the end of this process, all_nodes contains 1, 2, 3, 4, and child_nodes contains 2, 3, 4. To find the root, we compute the difference all_nodes, child_nodes, which gives us 1. Since this set contains exactly one node, we conclude that the root node is 1. This example highlights several key insights about the problem. First, the unique property of a tree is that it has exactly one root node, which is not a child of any other node. This property enables us to use set operations to isolate the root efficiently. Second, using sets for all nodes and child nodes is computationally efficient. Operations like subtraction have a time complexity of O(n), where n is the number of edges. Third, we need to account for edge cases. For example, if the input list is empty, there are no nodes, and hence no root. If the difference between all nodes and child nodes results in multiple nodes, the input does not represent a valid tree. Similarly, if the input contains cycles, the algorithm will fail because cycles violate the tree structure. For data structures, sets are ideal for this problem due to their ability to handle duplicates and perform fast membership checks. Tuples in the input list provide a concise way to represent edges between nodes. Analyzing the complexity of this algorithm, we see that the time complexity is O(n), where n is the number of edges in the tree. This is because we iterate over all edges once and perform set operations, which are linear in time. The space complexity is also O(n), as we store all nodes and child nodes in separate sets. To optimize further, we could use a single dictionary to count in degrees, which represent how many times a node appears as a child. This eliminates the need for two separate sets. In the alternate approach using in-degree counting, we initialize a dictionary to store in-degrees and iterate over each edge to increment the in-degree of the child node. After processing all edges, the root can be identified as the node with an in-degree of 0. This method also has a time complexity of O(n) and a space complexity of O(n), but it simplifies the algorithm by reducing the number of data structures used while maintaining the same efficiency. This solution addresses the problem of finding the root of an N-Ary tree. The root is defined as the node that is not referenced as a child by any other node. Step-by-step explanation. 1. Node class. The provided node class represents each node in the tree. It stores the node's value, val, and its list of children. 2. Find root function. First, we initialize a variable value _sum to 0. This variable will help us calculate the net sum of all node values, considering both parent and child relationships. We iterate over all nodes in the tree list. For each node, we add its value to value _sum. Additionally, for each child of the current node, we subtract the child's value from value _sum. This process effectively cancels out all nodes that appear as children, leaving only the root node's value. 3. Root identification. After calculating the net sum, we perform a second pass through the tree list to locate the node whose value matches value _sum. This node is the root of the tree. 4. Edge cases. If the tree is empty, the function will return none since no root exists. The algorithm assumes that the input forms a valid tree structure, so there will always be exactly one root node. Complexity analysis. Time complexity, O(n). The algorithm traverses all nodes twice, once to compute the net sum and once to identify the root node. Space complexity, O(1). The solution uses a constant amount of extra space, as value _sum is the only auxiliary variable. This approach is efficient and avoids the need for additional data structures, leveraging the mathematical property that the root node's value remains uncancelled in the net sum calculation. Here, we start the Java implementation for finding the root of an N-Ary tree. First, we define the node class, which represents the structure of each node in the tree. Each node has an integer value, val, and a list of children nodes. We provide 3 constructors for flexibility, one with no arguments that initializes a default node, one that accepts just the value, and another that accepts both the value and the list of children. Next, we define the solution class, where the main logic will reside. Inside this class, we implement the findRoot method, which takes a list of all nodes in the tree as input. To begin solving the problem, we initialize a variable, valueSum, which will help us calculate the difference between the total values of all nodes and their children. This approach leverages the property that the root node's value appears only once in the tree, while all other nodes' values are subtracted as they are referenced as children. Now, we traverse through all the nodes in the tree using a loop. For each node, we add its value to value sum. Then, we iterate through the node's children and subtract each child's value from value sum. By doing this, we effectively cancel out all non-root nodes, since each non-root node's value is added once as a node and subtracted once as a child. After the traversal, the value sum variable holds the value of the root node. To identify the root, we loop through the tree once more and check which node has a value matching value sum. When we find the match, we return that node as the root. Finally, we include a safeguard to return null in case no root is found, though this is an edge case and typically not expected with valid input. To solve this problem, let's start with an example of a tree that consists of 3 nodes. In this tree, node 1, which has the value 1, is the root. It has 2 children, node 2 with the value 2, and node 3 with the value 3. Both of these child nodes have no further children. The input represents this tree as an array of nodes. Now, to determine the root of the tree, we initialize a variable value _sum to 0. The goal is to iterate through all the nodes, adding their values to value _sum while subtracting the values of their children. Let's begin with node 1. Adding node 1's value to value _sum gives us 1. Then, we subtract the values of its children. First subtracting node 2's value results in -1, and then subtracting node 3's value further reduces value _sum to -4. Next, we process node 2, which doesn't have any children. Adding its value updates value _sum to -2. Finally, we handle node 3, which also doesn't have children. Adding node 3's value to value _sum gives us a final total of 1. At this point, value _sum represents the value of the root node. To identify the root node in the tree, we perform another traversal, looking for the node that has a value equal to value _sum. In this case, node 1 matches, so we return node 1 as the root of the tree. The final output for this example is node 1. Now, let's move to a second example with a more complex tree structure. This tree has 4 nodes. Node 4, with the value 4, is the root and has a single child, node 2. Node 2, which has the value 2, has 1 child, node 5. Node 5, with the value 5, has a child node 6, and node 6 has no children. The input for this tree is represented as an array of these nodes. Here, we repeat the process of calculating value _sum. Starting with node 4, adding its value gives us value _sum equals 4. Then, subtracting the value of its child, node 2, reduces value _sum to 2. Next, for node 2, adding its value brings value _sum back to 4, and subtracting the value of its child, node 5, results in -1. Moving on to node 5, adding its value updates value _sum to 4 again, and subtracting the value of its child, node 6, reduces value _sum to -2. Finally, for node 6, adding its value brings value _sum back to 4. After the loop, value _sum is 4, which corresponds to the value of the root node. To identify the root, we traverse the tree once more and locate the node with the value 4. This matches node 4, so we return node 4 as the root. The final output for this example is node 4. For the last example, we consider the simplest case, a single node tree. Here, the tree consists of just node 7, with the value 7, and no children. The input for this tree is an array containing only this node. As before, we start by initializing value _sum to 0. Since there is only one node, adding its value directly results in value _sum equals 7. With no children to subtract, the loop ends, and value _sum remains 7. At this point, we know that the value of the root node is 7. Traversing the tree, we find that node 7 has the same value as value _sum, so we return node 7 as the root. The final output for this example is node 7. To analyze the time complexity, we start with the first loop. In this loop, we traverse all nodes in the tree list. For each node, we add its value to the variable value _sum. Additionally, we process all of its children by subtracting each child's value from value _sum. If a node has k_I children, the time taken for that node is proportional to 1 plus k_I, where the 1 accounts for adding the node's value and k_I accounts for processing its children. Across the entire tree, the sum of all children is equal to the total number of edges in the N-Ary tree, which is N1. This means the total time complexity for the first loop is proportional to the number of nodes, or O(n). In the second loop, we iterate through the tree list again to find the node whose value matches value_sum. This involves a single comparison per node, which takes O(1) time per node. Therefore, the total time complexity for the second loop is also O(n). Combining these two loops, the time complexity of the entire algorithm is O(n). Now, since the two loops are executed one after the other and not nested, their time complexities simply add up, resulting in O(n plus n), which simplifies to O(n). Moving on to space complexity, the algorithm is designed to use constant extra space. The input tree list is provided as input and is not duplicated or modified, so it does not contribute to additional space consumption. For auxiliary variables, we only use a single integer, value_sum, which requires O(1) space. Furthermore, we do not employ any additional data structures like hash maps or arrays. Since the algorithm avoids recursion, there is no extra stack space required, making the overall space complexity of this solution constant at O(1). Let's compare this approach to a brute force method. In a naive solution, we might maintain a set of all nodes, iterate through each node and its children, and remove child nodes from the set as we go. The node left in the set would be the root. While this approach also has a time complexity of O(n), due to traversing all nodes and their children, its space complexity would be O(n), because of the additional set used to track nodes. In contrast, the current approach achieves the same time complexity of O(n), but it is much more space efficient with a constant space complexity of O(1). This makes our approach preferable, especially for scenarios where memory usage is a concern. Finally, let's analyze the best, average, and worst-case scenarios for this algorithm. Regardless of the structure of the tree or the distribution of its nodes, the algorithm must process all nodes and their children. This means the time complexity remains O(n), and the space complexity stays at O(1) for all cases. Now, for a mathematical justification of the time complexity, consider that the first loop processes each node exactly once and iterates over all edges in the tree. Since a tree with n nodes has n1 edges, this results in O(n) time. The second loop also processes each node exactly once, contributing another O(n). Adding these together gives O(n) plus O(n) equals O(n). Space usage remains constant because no additional data structures are required. Therefore, we conclude that the time complexity is O(n), and the space complexity is O(1) across all cases. When working with N-Ary tree problems, there are several common pitfalls to watch out for. First, not accounting for all nodes in the input is a frequent oversight. If you miss processing even a single node, you might fail to identify the root or end up with an incorrect result. It's critical to ensure that all nodes are considered, as each one informs the overall tree structure. Another mistake is assuming the input is always valid. Some problems might include edge cases like cycles or disconnected components, which can deviate from a typical tree structure. Always validate the input and ensure your solution adheres to the given problem constraints. Inefficient traversal or redundant calculations can also slow down your solution. For example, repeatedly traversing the tree to determine relationships can increase time complexity unnecessarily. Instead, consider using optimized data structures like hash sets or dictionaries for quick lookups. Misinterpreting the relationships between parents and children is another challenge. Small errors, like flipping parent and child references, can cascade into incorrect results, so it's important to double-check the input format. Lastly, overcomplicating the solution can lead to avoidable bugs or wasted time. Often, simpler approaches are sufficient for identifying the root of a tree, so focus on clarity and efficiency in your implementation. Understanding the nuances of tree problems can make a significant difference in an interview setting. Recognizing patterns is key. Many tree-related problems boil down to understanding hierarchical relationships. For instance, the root node is unique because it doesn't appear as a child of any other node. Being able to identify these patterns quickly can save time. Additionally, addressing edge cases is crucial. Always clarify constraints with your interviewer. Ask questions like whether the tree can contain cycles, multiple roots, or disconnected components. Knowing these details upfront allows you to tailor your solution appropriately. Spacetime complexity is another critical focus area. Interviewers are often interested in how efficiently you can solve the problem. For example, using a hash set to track child nodes allows you to achieve O(n) time and space complexity, which is optimal for most tree problems. Lastly, clear communication is essential. Walk your interviewer through your thought process, explaining why you've chosen a particular approach and discussing any trade-offs involved. This not only demonstrates your problem-solving skills but also shows your ability to think critically and prioritize effectively. Certain problems on LeetCode share similarities with finding the root of an N-Ary tree, and reviewing these can help solidify your understanding. For instance, LeetCode 310, Minimum Height Trees, focuses on identifying the centroids of a tree, which involves hierarchical relationships similar to finding a root. LeetCode 136, Single Number, introduces the concept of identifying unique elements, often using techniques like XOR that can be adapted for tree problems. LeetCode 207, Course Schedule, tests your ability to detect cycles and manage dependencies, which is highly relevant if the tree structure resembles a directed acyclic graph. Lastly, LeetCode 1123, Lowest Common Ancestor of Deepest Leaves, is another tree problem that emphasizes understanding hierarchical relationships. Alongside these related problems, alternative approaches can further enhance your toolkit. Using a hash set, for example, allows you to efficiently track child nodes and identify the root without redundant calculations. For more complex scenarios, a union-find algorithm is useful for validating tree structures, such as ensuring connectivity or detecting cycles. In cases where the tree is represented as a directed acyclic graph, topological sorting can help identify the root or resolve dependencies. These methods provide flexibility depending on the specific problem constraints. When solving tree problems, it's important to weigh the trade-offs between different approaches. Brute force methods are often simpler to implement but come with higher time complexity. For example, repeatedly traversing the tree to check relationships might result in O(n)² time complexity. Optimized solutions, like using hash sets, reduce this to O(n), but may require additional memory. Another trade-off to consider is readability versus efficiency. Highly optimized solutions can sometimes be harder to understand, especially under the pressure of an interview. In these situations, prioritize clarity and correctness in your initial solution. Once you have a working implementation, you can discuss potential optimizations with your interviewer. This approach not only demonstrates your ability to write clean, maintainable code but also shows that you're capable of improving efficiency when necessary. Balancing these factors is key to crafting a solution that is both effective and well-suited to the problem at hand. Great job working through this problem. We've learned how to identify the root of an N-Ary tree using an efficient approach. Remember, understanding the structure of the data and its unique properties is key to crafting optimal solutions. Don't forget to practice similar problems, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!